Hi everyone, my name is Omar and I'm going to present my NIER paper about debugging the undebuggable while multi-fault program break debugging and repair tools. Um, in fact, most of the existing state-of-the-art debugging and repair tool assume one fault at a time and do not take into consideration or account the fact that the fault may interact with each other. So in this work, we consider the problem where the program may contain multiple faults, and these faults may interact with each other in different ways. For example, one fault may mask or hide the effect of some other subsequent fault in the program or in a particular execution of the program. A fault may cascade up faults. Two fault may uh, um, triggered in the same execution so that the behavior of these two faults get combined and produce a new erroneous behavior that is novel and cannot be triggered by any of these individual faults. For example, fault FL1 here may influence the behavior or the visibility of fault F2, and fault F2 may also mask fault, the behavior or hide the effects of fault F3. So in real world programs, faults do interact with each other. They affect the visibility and the behavior of each other. But the current repair and debugging tool mainly consider independent faults or do not model this scenario where faults or multiple faults may interact with each other. So if you try to use one of these debugging tool or repair tool and try to debug a multi-fault program and allow these multiple faults to interact, you will see that these debugging and repair tools struggle to identify or locate these faults and generate feasible or correct patches for them. But in this work, we are interested in studying the question why debugging and repair tools struggle with a multi-fault program. And we find the best way to address this problem is to develop a formal model. So the goal is to formally answer the question why multiple interacting faults mislead a repair tool or debugging tool. So the formal model that we developed, model two aspects of the fault. One is the behavior, and the other is the visibility. So we try to model how one fault can affect the behavior or the visibility of the other faults. And we consider four different types. For example, independence, where two faults trigger independently, so they do not affect each other. In masking, where the earlier fault hide the effects of the later fault. Synergy, two faults, they amplify each other and produce a novel failure. Oral cascading, where FLI enables FG. So our formal model is a behavioral feasibility model and allow us to reason about the fault interaction. In general, we find that multi-fault programs are indebuggable in the general case. And mainly tools assume fault independence, both in debugging and repair tools. So if the program under analysis contains multiple independent faults, then yes, debugging tools can expose or detect these independent faults. Similarly, for repair tools, if the faults are independent, they can analyze and generate patches for them. But if they are interacting with each other via masking or synergy or other type of interaction, these tools will struggle. The key implication of this analysis or study is that for multi-fault localization, we need to develop mechanisms to detect the masking and the synergy. One way is to apply mutation-based testing. For multi-fault APR, we need to develop orchestrated repair techniques that respect dependencies and the interaction types that we discussed. And we find that we need to reason about the fault as a network of influencers rather than an isolated faults. One way to address this issue is to bridge the power of informal model with the AI-driven debugging. So in this work, we model fault interactions. We develop a formal model that enables us to understand and study different interaction types and to figure out why the existing program analysis tool is struggling with this kind of faults. And we guide multi-fault debugging and repair tools toward making them debuggable. This concludes my presentation. Thank you.